Hi, I'm Ms. Boom, and today we'll be looking at derivatives of circular functions. When the domain is measured in radians, our circular functions have derivatives. We're going to look at these three today. The derivative of sine x is cos x, the derivative of cos x is negative sine x, and the derivative of tan x is 1 over cos squared x, or sec squared x. Let's practice these. So we said the derivative of sine x is cos x, but what about if we have a constant in front of x? Let's call this constant k. Then the derivative of sine kx becomes k cos kx. Let's practice. So if we had sine 2x, what would it become? It would be 2 cos 2x. What is the derivative of sine 7 theta? It would be, take the 7 to the front, 7 cos 7 theta. Now for cos kx, we said that it will become negative k sine kx. So if we had cos 7 theta, it will be negative 7 sine 7 theta. And likewise, if we have fractions, we have to take the fractions to the front. So the derivative of cos x on 2 would be negative half sine x on 2. What about tan theta? We said it's equal to this, 1 over cos squared x, or sec squared x, so these two are equivalent, and these two are the derivative of that. So if we had a constant, again we'll put it at the front, so the derivative of tan 7x will be 7 sec squared 7x. 3 sine 5x, which of these are we following? That one over there. So we'll take the 5 to the front, 3 times 5 is 15, and sine becomes cos, so 15 cos 5x. What about half cos 4x? So we know that cos becomes negative sine, and take the 4 to the front, 4 times a half is 2, so we have negative 2 sine 4x. What about half tan 4x? Well, we know tan becomes sec squared x, take the 4 to the front, 4 times 5, again it's 2, so 2 sec squared 4x. What about when we have things like that, 2x minus 3 in the bracket? Well, we don't have to worry about the 3, we just have to worry about the 2, the number in front of x. So this becomes 2 cos 2x minus 3. Likewise, if we have cos, remember cos becomes negative sine. So when you take the 2 to the front, don't forget the negative from the derivative. So negative 3 times negative 2 becomes positive 6 sine 2x plus 1. Now that we've looked at the basic, let's apply this to other rules that we've learned in previous lessons. We're going to look at the chain rule. Remember, we derive g of x and then multiply it by f dash g of x. Now here we have sine squared x, which is the same as writing sine x squared. So our g of x is sine x, deriving sine x will become cos of x. And now something squared, when we derive that, we obtain 2 to the something, to the power of 2 minus 1 is 1. So it just becomes 2 sine x. And so our derivative of sine x squared becomes that times that. So 2 sine x cos x, and it doesn't matter if you write 2 cos x sine x, it doesn't matter what the order is. Also, you can skip this line over here and just go straight to the derivative. Next we have cos squared 7x. Now that we have a constant, we have to derive with the 7. So cos 7x, when we derive it, becomes negative sine x, and the 7 comes to the front as well, so negative 7 sine 7x. And deriving something squared, again bring the 2 to the front, so we have 2 all of that to the power of 1. And our derivative of cos 7x squared becomes negative 7 times 2 is negative 14 sine 7x cos 7x. Let's do slightly harder examples. So tan 7x plus 11 all cubed becomes, well, the derivative of tan 7x plus 11 is sec squared with a 7 at the front. So 7 sec squared 7x plus 11. Now f dash g of x, now something cubed means bring the 3 to the front, and then 3 take over 1 becomes squared. Now we combine these two. Again, you can skip this line, go straight to the derivative. So the derivative of 10 cubed 7x plus 11 is 3 times 7 is 21. 6 squared 7x plus 11 and 10 squared 7x plus 11. What if we had 10 7x to the power 5 plus 11? Is this and that previous example identical in terms of the way it gets derived? Not quite, because the 5 is next to the x. It's not 10 to the power 5, but it's x to the power 5. So in other words, we have 10 and then we have g of x in here, whereas g of x was part with the 10 in the previous question. So deriving g of x means we're deriving just what's in there and we ignore the 10 at the moment. So the derivative of g of x would be 7 times 5 is 35, take away 1 from the power is 4, and the 11 disappears. Now f dash g of x would be this red part here, so 10 becomes sec, and because g of x is all of that, we don't touch it, so it just becomes, we keep all of that together. Now putting those two next to each other to find the derivative, we have 35 times 1 is 35, x to the power 4, sec squared, and all of that in the bracket. Have a look at these two examples again and notice the difference between when g of x is 10 itself and when g of x is the thing in the bracket. So I put these two examples right next to each other so you can practice them again and make sure that you get the correct answer. Again, slightly more difficult examples. Now we have exponentials. So what happens if we have z of x e cos x squared? And now we're looking for the derivative of all of that at pi over 2. Now recall that the derivative of an exponential is, so e to the hx is the derivative of h of x, and then just copy out e to the h of x again. So we can see that at the moment we have e to the cos x squared. So h of x is cos x squared, but cos x squared is actually a combination of cos and another function. So we can use the chain rule for this. So let's derive g of x, which is x squared. So the derivative of g of x is 2x. Now, cos x, the derivative of cos x, we know is negative sine, and because we have x squared, we have negative sine x squared. So right now, this part is just deriving h of x, and we're putting it at the front. So now we have the derivative of e cos x squared becomes, so this and this goes at the front, so negative 2x sine x squared, this times this. And now we copy out that bit, e cos x squared. And then have we answered the question? Not quite, because it's asking for the derivative of pi over 2. So all we do is substitute where we see x by pi over 2, and negative 2 times pi over 2 just becomes negative pi, and we have sine pi over 2 squared. And then e cos pi over 2 squared. What about e sine squared x? Now we're going to derive it at pi over 4. So here again, we have a different concept. We have e sine x squared. So that square is on the outside. Notice that g of x is inside cos, and now g of x is part of sine. So deriving g of x, this time we have, well, sine x becomes cos x. And the 2 means bringing the 2 to the front and keeping sine x. And so the derivative of h of x, so the thing at the power of e, we have, so the derivative of e sine squared x, we have cos x times all of that, so 2 sine x cos x, and now we write that next to it, e sine squared x. And at pi over 4, the derivative is just square root of e, because we know that sine of pi over 4 is 1 over root 2, and squared means just half, so e to the power of half. And we know that derivative at pi over 4 is 1 over root 2 times 1 over root 2, which is half. Half times 2 is 1. So 1 times e to the power of half, which is root e. Thank you for watching, and have a practice of the questions that you found more complicated. I'll see you next time. Bye.